Yeah, so the talk today would be specifically about how language models or code language models are not well equipped to handle frequent version changes in like popular libraries or packages or just code in general. So without further ado, let's talk about a simple scenario. So imagine you are a software developer, right? You write like you do all the heavy duty for writing the code for a particular library or a package or something internal that you use at the company, and then you mature it, right? Like software is a evolutionary a modality, so it keeps evolving over time for whatever reasons that might be, to fix bugs or improve performance or add more utilities. And then that's how you grow as a developer or a coder, or even if you're from academic research purposes, the cycle is the same. And now you basically have a lot of people, like from going from here to here. Uh, the the package has evolved substantially, and then you have a lot of users who use that library or repository, request for changes or updates, and then subsequently a lot of version keeps updating of this package. And imagine you as the software developer had gone on a holiday, so you had not been exposed to all the changes that had been made to this particular package. Now you come back and you're kind of in trouble because you see that the state you had left the package in maybe a few days ago has completely changed since your time of departure. And this is a problem I'm sure a lot of people face, especially people who are actively using a specific package. They most likely keep tabs on what is changing, what is improving, and part of it also is very important in the way we document these updates. So as you could see, like when PyTorch makes a pretty big release, they have a very extensive documenting blog post which provides the details of everything that they have changed, so that people who are using it have a seamless transition, right? That is for us as humans because um, I mean, software engineering or coding is a practice that has evolved over many decades. So we have been attuned to this process. But unfortunately, language models are just quite not there yet, right? So I'm sure this question is out there in media, especially these days in media, with like the current trend of new foundation models out there, that AI is going to replace software devs, right? Like it's for sure becoming a redundant job, and people are soon realizing that okay, our jobs are a threat because we have models like DeepSeek or ChatGPT who can just like come over and do the exact same thing at a fraction of the cost, right? And you must have seen that this has a lot of implications, not just for you, but in global economy, like Salesforce CEO saying that we might pause hiring for junior dev engineers because agentic frameworks are so good. Um, so this will certainly have an impact. But the answer to this question, whether AI is going to replace software devs, well, not likely in the recent time. And first of all, because code is volatile and highly dynamic, which we understood from this example. Um, so the cycle is basically more a library gets popular, more people use it, more user give feedback, and the library undergoes more updates and releases. So it's a iterative loop. And this inherently demands a mechanism that can allow the language model to continually update, its knowledge base on what it has seen of that library, and then also to have an ability to remove memory pertaining to certain legacy packages. So you must have heard that, or must have seen like a lot of popular packages. They have legacy versions which are depreciated and not encouraged to use unless you are someone who's using a Power 9 architecture. Then good luck. But But generally, this is what we would expect an ideal language model to do, but we are far from that ideal language model state. Okay, so let me motivate this further. So if you look at the year-over-year version releases of popular packages, like I'm sure people here, given your expertise and background, must be familiar with all of the packages in this graph: PyTorch, Transformers, NumPy, pretty standard libraries in our field. They have undergone quite substantial number of version updates. As you can see, like some of them cumulatively have undergone more than 100. um, and that's quite fast, right? That's a very rapid growth. I mean, I agree that not all of these version updates are major releases. They can be like nightly versions or like test versions. Uh, so it's not like every version is a significant different version than its predecessor, but you have to account for the fact when you take it cumulatively, the 2023 version will look substantially different than the 2021 version, which is expected because the field innately demands such a rapid pace of growth. So let's talk more statistics. So Stack Overflow did a survey in 2023. I'm sure the numbers reported in the 2023 survey are now significantly inflated to adjust to 2024 dynamics. But in 2023, at least 70% of the participants who were part of the survey said that they already use and plan to use AI coding tools like Copilot. I'm sure the audience here have used once at least Copilot or regularly use Copilot. I would expect that if Visual Studio Code is your preferred editor. Um, and not only Stack Overflow, this is pretty common. Like across GitHub as well, GitHub did its own internal statistical benchmarking, stating that in 2023 there was a 27% year-over-year growth in the number of projects created, right? And these projects also span like libraries as they get popular. And across this growth, there was nearly 4.5 billion contributions. That's humongous, right? So um, I'm sure machine learning and deep learning libraries account for a significant number of these contributions. So that is basically the TLDR of the state that we are in terms of package management. We have packages which undergo rapid version change, and we have language models which unfortunately have been trained on a static data set, right? So it doesn't seem like a good marriage. So what is the static data set? This is usually a data set like the stack. Again, if people here are working on code generation models or code benchmarking, they must have heard of this data set. It's a data set that was contributed by this organization called Big Code and Hugging Face and ServiceNow and a few other people in the field. It's a pretty comprehensively large data set scraped off of GitHub. However, it has a cutoff date, so it has been collected since up until the year 2023. If I remember correctly, it's September 2023. So that's the Stack V2. There's also Stack V1, which was its predecessor. But most, if not all, the famous language models explicitly for code that you will see out there have been trained on this Stack V2 in combination of some other data set. But Stack V2 is probably the comprehensively most largest. But as I said, innately it is having a cutoff date. So 2023 is when it stopped collecting the data. 2023 is up until what the model has been exposed to. So any version, any library, anything that has come beyond 2023 is most likely OD to this model. And we don't want to retrain, right? Like I'm sure the narrative around computers getting cheaper, language models are becoming easier to train is all good and fine, but nobody is interested in retraining especially to adapt to new packages. Not only this, but we should also demand to highlight that a lot of the current benchmarks that we have in code language models, especially like if you have heard of human eval plus, big code bench, they are all very static-esque, which means they train them, uh, their objective is to test the language model or the code language model specifically on static repo-based problems for tasks like code editing or reasoning from the code, or just like debugging and yada yada. So basically, none of them explicitly try to see whether these language models can even adapt to you know version changes. That is where we propose our work, which is called GitChameleon. So I'm just going to take a pause here. I want this to be interactive, so if there's any question up until now, feel free to ask. If not, I will move on to what our work is on specifically. I can't see the chat or the meeting room, so if one of the organizers can just tell me if
Yeah,
everything is fine.
so yeah, sure. I think I don't see any questions in the chat. Yeah, feel free to raise any questions in the chat, folks. Like, so yeah, I think you can go ahead. I'll let you know, Diganta, if there are questions.
Okay, perfect. Thanks.
Yes.
Yeah, so our work, which is based on this aspect of evaluating code language models if they're capable of handling version change. So, as part of the work, we have to first construct a benchmark, which we call as Git Chameleon. So let's see what this benchmark does. So let's compare it to already existing popular dataset slash benchmarks in code language models. As you might have been aware of from exposure to code language models, if people are here working on that, human eval apps or DS1000, Big Code Bench, these are quite the standard ones. Of course, there's now the SWE bench, which is arguably probably the more of the important and hyped benchmark, but SweBench is usually a bit orthogonal to what we are trying to demonstrate. And also, SweBench is very, very focused on being demonstrated by agentic framework performances. While agentic framework would be an interesting topic in this narrative, we explicitly are only looking at static code language models like on their own, like as a standalone model. So all of these data sets out there, they test various aspects of code language model performance that might be, doing certain problems like from lead code, for example, or reasoning about the flow of a code, or improving a code, like improving the execution graph of a code, or just resolving certain bugs, and many more basically. And some of them are handwritten, some of them are derived from competitive benchmarks like lead code, um, and some of them are repository specific, so they are repo level code manipulation benchmarks. But usually we, from our exhaustive literature review, could not find one benchmark that met all the criteria, which is that it is library specific, it is also version specific, which means it is conditioned on different version releases. Third of all, it is execution based, which means we are not testing it against hard metrics like exact match. We are rather testing it from a unit test perspective. And then also that they are real samples, which mean they are constructed off of real version changes in real libraries. There are some which have this version change and have examples pertaining to it, but they synthesize this change using a language model. So they are not real library changes. So as part of that, we collected this data set of 116 Python only problems, which were completely handwritten. They were LLM assisted for us to parse them and verify whether the samples were good enough to be included in the dataset. And it meets all the criteria. So it is library specific, version specific. It has handwritten unit test for evaluation, and it is all based on real changes. So TLDR is GitChameleon is a benchmark that tests code language model ability to write version specific code. And as I said, it's Python based only, and it includes most of the popular machine learning and data science libraries that you might be familiar with, called like PyTorch, NetworkX, Pandas, NumPy, and more. Okay, let's talk about how comprehensive this data set is, because I'm sure when you look at the numbers here, they might not look as impressive as compared to some of the other data sets, because okay, like it's just 116 problems. But we can assure you the 116 problems are pretty difficult. Not to take it lightly. So statistics. Okay, so we have quite a few libraries, finite of them, all of them in the domain of machine learning. So everything you must have already used or heard of, like we have Gradio, PyTorch, NetworkX, AC, GeoPandas, and more. And we sample this from 2014, 2014 being the earliest sample version that we encountered, up until 2023, and then the bulk of the samples come from the release year of 2021. Okay, remember now I said before on that the stack was cut off at 2023, and I highlighted the problem that we cannot expect the language model to address issues that are pertaining to versions released beyond the cutoff date of the stack dataset. So why didn't we include samples beyond 2023? The reason we didn't want to do that is because we want to first explicitly test if the language model currently, which has seen all the versions within the training window of the stack, which is up until 2023, can even handle version change problems for the versions it has seen within its training window. So making this a pretty much ID problem, right? So we expect that the language model that has been trained on stack would have seen torch 1.5, 1.6, 1.7. So our expectation, or rather what we want to evaluate, is can it even solve problems when migrating from 1.5 to 1.6, because it has seen both the versions, right? So we expect that it knows what has changed from 1.6 to 1.7. um, Now, when I was talking about it, I actually recall the actual word I should have used for this problem is migration, right? And I can give you more instances. There are colleagues of mine who work at firms where they have clients from the finance sector, where they're banking companies who want to do Java migration, basically to upgrade their software backend. And it's quite a tedious process. And we all know um, how rather unlinted fintech code bases are. So definitely, if we can deploy a language model to address that problem, it would be really nice. But so that is a part of what we are trying to test here, is if it has already seen the version, can it handle the problem? And we categorize all these problems based on what type of change had occurred. So there can be changes to the argument or attributes expected by a particular API call. There can be change to the function name itself, of the target function. So something like XYZ in PyTorch changed from XYZ in 1.5 to YZ in 1.6. So if you're using 1.6, you want to call that function using torch.yz. Um, there's also semantic change. Now, semantic change is a bit of a loose term. The reason we call it semantic or behavioral, which means that the function now behaves in a different way than its previous version. So for example, if it is returning more items, so like for example, if in version 1.5, it was returning only a single tensor, like return X, but in version 1.6, it is returning a tuple of tensors, so return X comma Y. If you were using version 1.6, but just retrieving um, a singular value from that function, it will break because it's expecting to return a tuple, right? So that is what semantic changes are. And then there is the obvious change, which is new features. So like certain features were not available in previous versions. I remember from a dataset to there's a function called touch.special, if I remember correctly, and that was not available before 1.5 or 1.4, and people had to use NumPy to utilize it. But now that it is available, you would rather use the inbuilt function, right? So that is the four categories that we are looking for. Now, one category that we exclude is precision-based changes. So like a lot of the times these libraries are very well matured, so they don't need as external facelift as you would require, but they rather undergo a lot of backend low-level changes, which improves performance, basically, like essentially improving the numerical precision of softmax, for instance. We do not take these changes into consideration. The reason is because the code itself doesn't change, it's only the performance of that function at its low level changes. So from a code generation model writing perspective, it makes no difference to write it in its previous version versus in its current version, right? It's always going to be correct. So as you can see, this is the reason why it was so difficult to even collect the 116 samples, because we have to manually go over each library, look at each of the version releases, go over the documentation, make the code diff, basically see what changed in its previous file to its current file, and then decide whether it is an appropriate change to be included in the benchmark. Okay, so how's the collection framework looking like? So
Diganta, there's a
yes,
question in the chat.
yes.
Shashank, do you want to maybe tell it right now?
Yeah, sure. So, I guess this is actually something I was drafting before you. I guess you had asked if does anyone have any questions. So this is from back then, just for context. So,
Sure.
basically, I wanted to ask. So you mentioned that there's a lack of up to date data that or code data that goes into the training of these LLMs and all these different coding assistant models. So,
Right.
would you say that that's still a problem given the the trend of these increasing context lengths at a lower cost? Like you have recently this Titans came out, you have Transformer Square, like all these people they're basically trying to reduce the cost of increasing the context and therefore enabling people to use more context. So say you have some changes or you have something that's if you have like a million context length at really cheap cost, then you could just pass the library itself, like based on the kind of changes that you would have to make, or pass the entire what do you say, repo. So like things like this, basically using RAG with these LLMs with reduced costs. Like,
Right.
would that
Right.
still be a problem? I mean, I'm assuming that the
Yeah.
stack would just be used to understand how to code in general, given that there are like multiple different types of styles and all that are in there. So through multitask learning, it's just learning how to code, the essence of coding, and through RAG, then you
Yeah.
could. I mean, yeah, I guess you understood what I'm getting at. Yeah.
Yeah, great question. In fact, we have results on this, like on this aspect exactly. Not, I would not call it pure RAG, but I will get to this. So I don't want to answer it right now because I'll just show you based on observation what we have, and maybe it will make it clear, and we can revisit this question at that point.
Yeah. Cool. Okay.
Okay, so collection framework, how do we collect these samples, or rather what the template looks like? So we have a task description. If you've seen like human eval or like similar coding benchmarks, they usually have this prompt or a description of the task. And then we have a starter code. So we give a head start to the model. So we basically remove any problems associated to erroneous package imports. Basically, sometimes language models hallucinate, like they might import a package that doesn't exist. So we basically remove that. We literally go straight to the function call, and we just keep the line which it has to edit as empty. So as a blank. So we expect that the language model will write inside that function within that starter code, right? And then we have expected result, and then we have assertion test that basically asserts the output of that function given after the model has correctly resolved the problem based on the task description. And we have assertion test to basically check whether it is matching. And this specifically is this example that you're seeing is from NumPy 1.25, if I'm remembering correctly. And what we do when we do the assertion test, we have dynamic environment creation. So we create the environment based on the package version that we ask for within the task description. So I'm not showing within the task description here the requested package version. This is just an example, but in our task description, we explicitly highlight which package version we want the language model to adhere to. And then upon the unit test that we construct for the evaluation, we dynamically create environments that have that specific version within that environment. So the assertion, the code will break if it doesn't adhere to that particular package change. All right, so let's look at results. So first of all, non-instruct. So base model performances ranging from as small as 1 billion to going as high as 70 billion. So pretty much all the popular models. Yes, I know people will ask for the latest DeepSeek models. We will get to that, but at the time of us publishing this work, these were pretty much the best base models out there. And we explicitly, if there was an option, we explicitly chose the Python version for a model if it was available, like CodeLlama having an explicit Python suite. We rely on that because all of our problems are Python based. So and we measured this metric called pass at 10 and pass at 1, and the T is basically here the temperature of the sampling that we use. And you can see the performance, like we can see that there is a scaling effect. Yes, models grow bigger, performance improves usually, but our pass at 1 is at 35.7 at the best, which is DeepSeek 33B. And if you compare this to other benchmarks, which I'm going to show later, this pass at 1 is pretty bad as compared to something as the best pass at 1 that you can obtain on Human Eval Plus, which is considered to be a pretty challenging benchmark. But what is more interesting is probably instruct performance, because most of the state-of-the-art models, or rather what you would use, would fall into this category. So this would include like GPT-4o, Gemini, Phi 3.5, Granite Code, and more. And this is a pretty big graph to digest, but let's look at the sizes. So the size range is pretty much the same. We have ranging from 1B up until like even MOE 16 by 3.8B, which is pretty big. But we also have like industrial models like GPT and Gemini. And now, in this case, we measure a few more things than what we were measuring earlier. So we measure, of course, the baseline performance, which is the basically the default prompt that we give to resolve that particular problem statement and expect the answer provided by the language model to be correct. And then we evaluate against the unit test that we have. Then we have error feedback, which is like one more cycle of prompting. So we give the baseline prompt to the model. We get its result. If it could not resolve that problem in its first try, we get basically the error trace, because all of our problems are execution based evaluation. So we get an error trace and we reprompt the model with the error trace and expect that it will understand what the error trace was and resolve the issue, right? So that is error feedback. We only do the error feedback for only those samples that it could not resolve. For the samples it could resolve, stays the same. So error feedback will always be lower bounded by baseline performance. Then we have greedy, which is basically greedy sampling. So don't have to explain that. And just for the sanity check, we also did zero sort chain of thought prompting. So you can see performance is not that good still. Like best performance we get is via Gemini 35.9 with error feedback. Even a model like GPT 3.5, which is pretty good a model, is actually not that good in baseline performance. It is 19.6 at pass at one, which is pretty low on this benchmark. Although not the lowest, we have observed that Llama 3.2 and few of the models are really poor at this benchmark. But overall, the trend is that models are just not good enough on this task. And the question you might ask is, should I even care about it, right? If OpenAI doesn't care about it, if nobody is caring about this benchmark, why would I care? Like, if they only care about showing on human eval performance or bench performance, if my model can do well on that, then my model can do well on GitChameleon. So the question is, can you bootstrap this by solving other benchmarks, basically? And the TLDR is no, you cannot. It's not even close. So if you look at the current hardest benchmarks out there, at least claimed by academics and the respective papers like Human Eval, Eval Plus, and Bigcode Bench. Bigcode Bench, I believe, is the latest of them all. I mean, there is some very weak correlation that yes, when model improves performance on Bigcode Bench or Eval Plus, it also improves performance on GitChameleon, but that's not strictly the case. Like the models which are good on human eval, like Llama 3.1 or even like Qwen 2, but they're pretty poor on GitChameleon. So it's not a guarantee that if you just do well on these existing benchmarks, you would do well on a task which is pertaining to version sensitivity. Okay, so let's dive a bit more into these results. That was a lot of numbers, so let's break it down into some categories. Let's look at the top graph. So we want to see basically all the samples from binned into different years of their corresponding version releases. So we have 2021, 2022, and 2023 to be the bulk of our data set. Like most of the samples are contributed from these 3 years. And you would also the uniformity of there is no uniformity rather of the samples from these versions across the years that would have been exposed to the language model. For example, if a version was released in 2023 April, then it wouldn't have had enough samples, like it wouldn't have had enough projects inheriting that version since 2023 April to 2023 September, until which the training cutoff was, for the model to have been exposed enough to that version as compared to something that would have been released in 2022, right? So our expectation is the model will behave similarly, like the model will be better on versions that it would have seen in more adequate numbers from projects inheriting it or just itself, and it will be worse on newer versions, right? So the trend is something of our expectancy, right? You can see 2021. So the darker shade here means the performance post error feedback, and the lighter shade bar here means the baseline performance, right? So you can see that 2021, which is accounting for a lot of samples and probably also had a lot of projects inheriting those versions, has models performing better, significantly better as compared to 2022 and 2023. So the hypothesis somewhat stands that as models are exposed to more data from those specific versions, they tend to do a slightly bit better. And which is fine, but we want to also look at what categories of changes do models behave superior or inferior in. One thing we found out for certain is that semantics level changes, which, as I explained before, means the behavior of the API has changed, or specific functions behavior has changed. It might be that it is now returning something else, or it is returning a different data type. Models are really poor on this category of change. They barely can handle this. And you can see like the scale of the x-axis, which represents parser 10 over here, is really, really poor on the semantics categorization. Although semantics account for less samples as compared to samples coming from argument or attribute changes, which is expected because most of the change falls into that or new feature category, and there are not as many changes in the semantics category. So you can like account for some bias here, but in general, the trend is that semantic level changes are just not well addressed. Okay, so if we were to look at the difficulty of the samples, then certainly with error feedback, the bulk moves basically, which means that more samples from the lower parser 10 range move to the higher parser 10 range, and that is shown on the right figure over here. If you look at each model, we show the baseline and the error feedback, and the x-axis is the parser 10 range binned into 3 bins basically, and we have the frequency of samples that fall into each of the bin, and you can see that there is some improvement, but it's not a lot. As you can see with Quen 2, we had 68 samples that was falling into the lower first bin of parser 10, and it only went down to 66, and there were 2 samples that went higher, right? So it's not like, oh, like just because I have error feedback, I can resolve all of these problems. So they're pretty hard problems innately. And further, you should know that error feedback accounts for one more cyclic prompting, so it accounts for extra cost, right? So I would not call it parser 10, I would call it like something like parser 10 plus 1, because I'm allowing the model to like try to resolve its issue one more time. Okay, so context level stuff, right? So we tried to basically see the performance on different like packages that we have in our data set. So Torch, NumPy, NetworkX being accounting for most of the problems that we have. And we saw that these models are not uniformly well across these packages, even for very popular packages that we expect that it would have seen a lot of examples from. Basically, like we expect that Torch would be a package that would dominate heavily in the stack, and it would have seen a lot of samples from Torch and packages like NumPy, but certainly not the case. Like it is actually funny that Code Llama and even Llama, we don't show it in this benchmark, actually is pretty poor on Torch, which okay, like that should not be the case from the standpoint of who created that model, but that is our observation. And one thing you should note is the bars are here different. So so we represent the darker bars as doc prompting and the lighter bars as baseline prompting. Now, what is doc prompting, right? So I believe Shashank was the person who asked for, like, oh, if we have really large context windows, we could just pass the library or the specific version, and like it should be able to derive what has changed and write the code, right? So we did something like that, which we call doc prompting, and that was simply giving the documentation of the function in its target version as asked in the problem statement. So that is what doc prompting is. So we have, like, let's say our problem is on touch.special, right? We expect that it would write touch.special or something similar, and that is specific to version 1.5. We literally obtain the 1.5 version documentation of touch.special, copy paste it into the prompt, and then the task description and the starter code. That is what tough prompting is. It doesn't help. It's often worse than just doing greedy sampling, actually. Um, that just highlights, to some extent, I would not claim it conclusive, that even though these models will have pretty expansive context windows, they still cannot understand, as of right now, what has changed, what I should do to adhere to the change, and write the correct solution. Now, I have a lot of hypotheses. I can get into why this is happening. Like, for example, tokenization might be an issue. And because also, like, there is no explicit, prior that is given to these models to understand what version they are looking at in the code. Like, for example, if you look at a lot of repositories, right, they do not necessarily have a setup.py or a requirements.txt, right? So when you encode those repositories as part of your data set, the language model has pretty much zero guidance to know what version that code is coming from. So usually it would break unless they have written good documentation, which I've tried to highlight that it is very important. Then the language model pretty much has, like, it, you are giving it a head start to not even understand what version changes even mean. But it's not just in this case. Like, we see some hints of this long context problem when we do error feedback. So we were like, okay, let's try to see what type of errors are usually resolved based on the baseline generation when we do error feedback prompting. And every category of error usually improves. Like, we reduce the number of breaking code on every category of error, usually like name, indentation, attribute or import or assertion error. But if you see the biggest that goes up, like with error feedback, the type of samples that really are hurt is when you increase timeout error. And this is happening because the error trace from the baseline generation is very long and very convoluted. I'm sure you have seen error traces which start at that line and then go internally into PyTorch and then like end at some point, and you're pretty much lost. And then you have to copy the last line which says, oh, this, and paste it on Stack Overflow and pray to God that somebody has encountered it and somebody has resolved it, right? So the language model is pretty much facing the same issue. It cannot understand the tree of the error trace and just like does something like, resolving a problem by writing an infinite loop. So we go into timeout error. So this is, in my opinion, a long context problem. I'm sure people who are more familiar with language models can properly define this phenomenon, but I would call it long context problem from my perspective. And also, like, this can be attributed to bad error trace templates for LLM parsing. So the error traces that are outputted by any code editor that you use are usually written in that template so that humans can read and understand it. So we can know, like, okay, this breaks at this file, and this file's content was being inherited in this file, and then we can basically backtrace to where it originated from and hopefully resolve it. But maybe this template is definitely not what a language model should rely on. Like, maybe it can be optimized, which is completely an open research problem. So, like, the question is, can we do improved prompting while doing error feedback? This is something we would love to do. We didn't do it as part of this project, but it would be really nice to see if that can be improved. So let's highlight the main findings. So current state-of-the-art code language models are not reliable for version-specific code generation. They suffer high degradation in performance when exposed to changes which are pertaining to semantics in any function or API call in popular libraries. And sure, error feedback can come to your rescue, but it will marginally improve performance and often come at a cost that you will see a lot of problems getting worse off because the models don't understand what the error trace is pointing to. What we want to do as part of the future work is that we want to do more samples, more models. I'm sure any R2 for this paper would be like, oh, 116 samples, super easy, not that difficult. So we are in the process of expanding this to 300 samples and hopefully get more models. So we'll definitely benchmark all the latest and greatest models that have come out recently since our paper was out there. Uh, and we're going to do a proper RAG baseline. So like instead of doing the doc prompting that I showed you, we're going to allow, retrieving the documentation from the web and accessing the web as part of resolving the problem. So hopefully it's gonna show improved performance beyond what we have already demonstrated with our best prompting techniques. And we want to do dynamic Git chameleon based on agentic frameworks. So, like in an ideal world, this benchmark should have a rolling window. So it should, keep rolling with new versions coming out. It should keep rolling because otherwise it doesn't make sense, right? If we only have this data set up until 2023, then in 2026 it becomes pretty obsolete because most of those versions that we had in 20 up until 2023 as part of the dataset will become legacy and nobody would get to benchmark on it. So ideal world, we want to have a agent that can retrieve samples for this benchmark, as new versions come out of these popular libraries, and then we have a rolling window for this benchmark, and it's not a static benchmark anymore. And as you saw that I highlighted that error feedback prompting is definitely not optimal, at least the way we did it. So hopefully we aim to improve that in future work. Yes, so that's pretty much it. I hope I resolved your questions, Shashank, or if you have further doubts, I'm happy to address. But this is our paper. It was accepted at DMLR at iClear last year. The QR code is to our paper, so feel free to check it out. The actual examples in there, I didn't want to show it because they're quite lengthy. But if you want to see what the actual samples look like or the actual generated output from these models, you can take a look at the paper. And this work was uh, done in collaboration with Mila, Max Planck, ServiceNow, Monash, University of Montreal. So yeah, thanks everyone. If you have any questions, feel free to ask.
Yeah, Shashank, go ahead.
Yeah. Hey, thanks for answering the question I asked earlier. I just wanted to actually ask a follow-up regarding that. So you mentioned you were giving it documentation of the code, or how to basically implement the improved or changed functional methods that it needs to access. But my question is, like in that documentation, were you also including like examples of usage? Like, for example, how it's like did it just describe, okay, what is the change, or what is this new improved what do you say, method? Like, okay, fine, pass these attributes. Like, is it just in plain like natural language? Is there an example that is going along with it? I was just curious about that.
Yeah, so as part of the doc prompting strategy, we only like provided the actual documentation. So if the documentation included an example, that will be provided. Sorry. Yeah, so we did not explicitly change the documentation, like to say, okay, like this is what was changed since 1.5 to 1.6, but we just, like whatever 1.6 documentation states of that particular function, we provided exactly.
I see. Okay. Also, one more question. Like, I think on the graphs where you were comparing performance,
Yeah.
like year-wise performance, like, is there any reason why you feel like the performance for 2021 for most of the models is way higher on average than like later years, like 2022 or 2023? Like, could it be correlated with the cumulative year-on-year trend that you were showing, where there are more changes, it's more rapid, so maybe the training data is also less. Like, what do you what are your thoughts on that?
Yeah. Yeah, I agree. my hypothesis is that 2021 has a lot of samples for the specific versions that we have from 2021, because we expect that uh, there were a lot of stable releases, and a lot of projects have inherited those versions. But something like in 2023 would have been much harder, because the cutoff is within 9 months of 2023, right? So there wouldn't have been enough projects created in 2023 versions that would have inherited those specific versions, so they wouldn't have seen enough samples. So we expect the performance is better in 2021 because there are more samples, and also, as you pointed out, there are less there are less release versions to handle it.
Right. And I think this is despite, I think in your graph where you showed the number of samples you took per year, I think the earlier years had way less samples as well, right? Taken. So well, that's interesting. Okay, thank you. Thank you for answering that. Yeah.
Yeah.